Before we move on to the problems associated with graphing radicals, we're first going to take a look at the parent function of a radical, or the parent function of a radical equation. So your parent function is y equals the square root of x. Now, I'm just going to go ahead and show you some stuff so that you can see exactly how this works and why certain things won't work when graphing a radical function. So normally I would tell you, go ahead and choose 0, 0 as your vertex or your starting point, and then two numbers both smaller and greater than 0. Now, if we plug -2 into the square root, what we're going to get is the square root of -2. You can't take the square root of a negative number, or at least not yet. We won't get into that until you hit Algebra 2 when we talk about imaginary numbers. So there's no real number that we can get out of the square root of a negative number. So there's nothing that can go there. If we plug in -1, we're going to have the same result. We're going to get an imaginary number, and therefore we can't actually do any graphing with this, at least not yet. So you can see that anything that gives us a radicand that is less than 0 is just not going to work. If we plug in 0, square root of 0 is 0. Then if we plug in 1, we get the square root of 1 is also equal to 1. Now what I would suggest is instead of using 2, you actually use a perfect square. The next perfect square up from 1 is 4. And the square root of 4 is going to be 2. And so now we've got 3 points that we can use to graph our radical function. We're going to go 0, 0. We're going to go 1, 1. So right now it looks like it's going to be a linear function, but it's not. Then we're going to go 4 and then up 2. So right 4 and then up 2. And so what we're going to get is actually basically a half of a parabola that's been turned on its side. So this is what a radical function is almost always going to look like. Now you could flip it and it could go off that direction. You could flip it downwards, it can go this direction. Or if you had a plus or a minus the square root of x, then you could also end up with something that looks like that, where you get a full parabolic looking graph. But for right now, all you're going to be doing is just this right here. So you only need 3 points at this point to graph your radical functions. Now, one of the things that you may have noticed when we graph the parent function is that our domain, or the number of x values that our graph was going to pass through, was limited. And that's because of the characteristics of the radicand. Remember that the radicand can never be less than 0. If the radicand is less than 0, then you're going to get an imaginary number. So the way that we check our domain is to take the radicand and set the radicand equal to 0. So your very last point is going to be whatever point is spit out when you work this problem out here. So if we do 3x minus 9, we get 3x is equal to 9, and so x is equal to 3. What this means is that our domain ends at the number 3. So if we were to graph this, what we would do is we would go 1, 2, and 3. This would be our starting point. So we would know that we could go to 3 or we could go to the right of 3, but we could not go to the left of 3. Any numbers that are less than 3 are not going to be in the domain of the function. So what this tells us is that the domain for this is going to be x is greater than or equal to 3, or if you put this in interval notation, you could say bracket 3, comma, and then infinity, and then close parenthesis. And that's going to be your domain whenever we're doing radicals. You're going to have some restrictions on the domain, and you're also going to have some restrictions on the range. On this particular one, the range on this one, you cannot go below 0. So if we were to do our range on this one, the range would be y is greater than or equal to 0, or you could do it in interval notation and say bracket 0, infinity, and then close parenthesis. And that's going to be both your domain and your range when we're doing these radicals. In the unit that we did on absolute value functions, you were introduced to the formula, the vertex form or the general form of an absolute value function. Well, we're going to use that again over and over and over again. We're just going to adjust it to whatever we're working on at the time. Right now, we're working on radical functions. So instead of it being y equals a times the absolute value of x minus h plus k, we now have y equals a times the square root of x minus h plus k. So all the same rules apply. A is still going to tell you what your stretch, compress, or reflect is. H, the opposite of h is going to tell you, or the opposite of whatever this value is going to tell you what your horizontal movement is. And the k value is going to tell you what your vertical movement is. So on the problem that we're given in the book, we've got y equals the square root of x plus 2. You can see that in place of the a value, we have a 1. So since the a value is a 1, there's no stretch, compress, or reflect that we need to worry about. So it's not going to be stretched vertically, and it's not going to be compressed down towards the x-axis. The h value, there is nothing that's being added or subtracted to the x. That means that our h value is 0. Then our k value is whatever is being added or subtracted to the radical itself. So the k value in this case is going to be 2. What that tells us is that our starting point is going to be the point 0, 2. So we want to go ahead and put that onto our xy chart. Then our maximum or minimum. Again, this is going to be based on the y. So we've got a, this is going to open, it's going to open in this direction because it's a positive 1 for the a value. So that means that we're going to have a minimum point at y equals 2. So we're going to go ahead and write in minimum at y equals 2. Now the domain is going to be what is going to make x, or what is going to make this radicand less than 0. So what we do is we take that and we set the radicand, it's got to be greater than or equal to 0. And so since we've already got this, x is greater than or equal to 0, there's nothing to do with the x. We know that the domain is going to be x is greater than or equal to 0. The range is just simply going to be, since it opens up, it's going to be greater than the minimum value, so y is greater than or equal to 2. Again, if you want to do this in interval notation, or if you're required to do it in interval notation, you're going to have 0, infinity, and then here you're going to have 2, infinity. Now, the next step in this process is go ahead and take the 0, 2, and let's put that on our graph. Now we need two values of x that are greater than 0. So we're going to go 1, and I'm going to go with, again, 4, because I want my radicand to end up being perfect squares, so that I don't have any decimals or anything like that to worry about when I'm graphing. So I'm going to plug 1 in here. So let me go ahead and get rid of this 1 there. The square root of 1 is 1, plus 2 is 3. The square root of 4 is 2, plus 2 is 4. So now I've got 3 points. That's really all I need in order to be able to graph this. So I've got 1 and 3, and I've got 4 and 4. And you can see that I've got the same basic shape that I had with the parent function. It's just been moved up 2 units. So here on problem number 4, we're going to exchange the k value for an h value. The one thing that's going to do is, instead of having an upwards or downwards movement in our graph, we're now going to shift it left and right. So let's go ahead and go through all of the things that we need, all of the information that we need to begin with. So our a value is going to be 1. Because again, we have nothing sitting out here. We assume to be 1, which tells us that there's no stretch, compress, or reflect. So we're going to put none. Now the h value, since we've got a 3 being added to the x, we're going to go the opposite of whatever is being done there. So since this is adding 3, we're going to say that the h value is negative 3. Then our k value, there's nothing out here. So that means that our k value is 0, and then our starting point is going to be negative 3, 0. So go ahead and go write this on your xy chart, and you can see that we know that the starting point is going to be negative 3, 0, and then we can come over here to our graph and we can plot that as well. Now this graph is going to open up again upwards and to the right, so we know that all of our x values are going to be greater than this point here. But before we get to the domain, let's go ahead and take care of the minimum or maximum. Since it's opening up, we know that we have a minimum, and that minimum is going to be at y equals, again, whatever this value is for y, that's going to be the minimum value for y. The domain, again, we could look at it as everything greater than -3 is going to be in the domain. But if you want to know how to check it algebraically, again, go to x plus 3 and set it greater than or equal to 0. And then when we do that, we can see that x is greater than or equal to -3, which is what we already knew based on the point that we've graphed. So we know that our domain is going to be x is greater than or equal to -3. And then the range on this is going to be the minimum value, but we're going to change that equal sign to greater than or equal to because we know that it's opening up. So we're going to go y is greater than or equal to 0. Again, if you were to do this in interval notation, you're going to have -3 to infinity and 0 to infinity. Coming back over here to our xy chart, we just need 2 more values to finish this off. So I need 2 values that are greater than -3. Here's the catch on this one though. Remember I've told you that you want your radicand to be a number that is a perfect square. So what you're going to be doing is thinking to yourself, what value of x is going to give me 1? What value of x is going to give me 4? So if we start with that value, what value of x is going to give me 1? Well, what do you add to 3 in order to get down to 1? You do -2. -2 plus 3 is 1. What's the square root of 1? 1. What value of x is going to get you to 4? Well, 1 plus 3 is 4, so you want to use the value of x at 1. Then you get 1 plus 3 is 4. The square root of 4 is 2. And again, what this does, by making sure that your radicand ends up being a perfect square, you're going to be dealing with only integers. You're not going to have to deal with any decimals. You're not going to get fractions out of this because we're dealing with square roots. So you're not going to have to deal with any decimals. That's really the key in why you want to use this method. So again, the way you want to think about this is what values of x are going to give you 0, 1, and 4. And if you do that, you're always going to get 0, 1, and 2 coming out for your y's. So now we just need to graph these. -2 and 1, and then 1 and 2. Connect the dots, and there you have your graph.